Okay, thank you. So today, what we are starting with is an area called calculus, and Isaac Newton famously created this when he was doing his laws of physics, so that he could laws of motion, and he used the idea of the derivative and the change in that. So he created this. So for us though, the derivative's the key thing, and so for us what we're doing, if we have a graph of some sort, a line of some sort, which is curved, and the function f of x, and if we, for example, have a point on that line, so this point here, we'll call it point P, and we want to know what is the gradient of that curve at that point. So this line here, this blue line, would be what we would call our tangent. So we want to know, how can we figure out what the gradient of that tangent would be? Now, normally when we'd be working out the gradients, so the gradient of anything is rise over run, or the rise is the difference in our y coordinates over the difference in our x coordinates. So that's how we would work out the gradient. Now, unfortunately, with the tangent, if we want to know what the gradient of the tangent here is at this point here, and I'm going to give the coordinates of this point P, let me write, I'll write the coordinates over here, would be x, so this value here, x, and the y value, I'm just going to write in function form, call it f of x. But we've only got 1 point. We haven't got any more than one, we've only got 1 point. So how can we work out the gradient? So what we can do is, we can say, okay, what if I have another point? And so let's say another point here, and I'll call this point B, and what I can do is I can work out the gradient of that easily enough, as if I know its x value, so x2, and the way I'm going to work this out, and this will become, what I'm going to do is I'm going to call the difference between those, that distance there, I'm going to call it h. So this second x value would be our original x value plus this h. Alright, so my point B, its coordinates would be, the x value would be the x plus h, and in function notation, f of, put in the x value. Now, quite clearly, that gradient's not the same as the tangent. However, what we can do is, looking at this graphic over here on the board, we can, if I get my head in the right spot, sorry, we can here, here's our tangent line, so there's our tangent line. So if I, and here's what's called A here, not, I used B on my diagram, not to worry. And the h is this horizontal distance here, so let's have a look at, there's that triangle, so this is this h here. So the vertical, this height there, would be those coordinates. So the coordinate, y coordinate of A, which is f of x plus A, minus the y coordinate of P, which is f of x, And so that's this side here. I'll do more of that in a minute. And then the difference in the x values. So if I make this side h smaller, that will move this point A. So let's make it smaller. So quite a bit smaller. And so the red line that's there, what do you notice about the gradient as I make h smaller?
It's more straight.
It changes. Yep, but it comes closer to the gradient of the blue one. All right, whoops, gone too far. And the blue one, the gradient of the blue one, is the one we're interested in. All right, so slopes, what's that one? Can't remember that one. All right, so here's the secant line. That's the red line, so that's this line. Straight line between those points on the graph, and the tangent line is 0.33. So start with h being a big number. You can see here their gradients are quite different, but as I go smaller, then those gradients become the same. All right, so this is what the derivative is kind of all about. It's all about coming up with a way that we can work out what the gradient of this curved line is. And in fact, we can do it for any curved line by using this idea. So we're still using, swing my camera back, I haven't got Eddie Wu's budget, so I have to do all this myself. So from what we've got here, our gradient of our line P to B is the second y value, and that's the f of x plus h, minus the first y value, which is our f of x, over the second x value, which is x plus h, minus the first x value, which is just x. So that comes to the denominator is just that h. And so that's our gradient from P to B. And what we know is, from looking at that diagram, is if I make this h smaller, then the gradient of what's the purple line here, the red line in that graphic, becomes closer to the gradient of the tangent. So what I can say is, as h goes towards 0, the gradient of that line, that secant, goes towards the gradient, the gradient of the tangent. Right, any questions so far?
Not yet.
Not yet? All right, so what are we doing? We're working out the gradient of this purple line here to approximate the gradient of that tangent. And if I make this h smaller, what does that do? That brings this point closer and closer. And as we bring the point closer and closer, the gradient of the purple line gets closer to the gradient of the blue line. Yes?
Yes.
We're all happy with that? So that's what we're doing. All right, so how can I write this? Well, the way we write this mathematically is this. We would say that the gradient of the tangent is equal to the limit as h tends to 0 of the gradient of the, B, not D, of the line joining those points P and B. All right. Or the limit as as h tends to 0 of f of x plus h minus f of x over h. Alright. So all this says, we've got, this is the gradient of a line joining 2 points on the graph. Make this h smaller and smaller, going towards 0, and that goes towards the gradient of the tangent, and the limit of that, if we could make h equal 0, then this gradient, the gradient between these points, and the gradient of the tangent would be the same. Yes? No? Maybe any questions about that? No? And this bit here, this thing here, is what we would refer to as, is known as the derivative. So this thing here is known as the derivative. So key thing about the derivative is that the derivative tells us about the gradient of the function. Which hopefully makes sense, seeing as, what did we start with? We started looking at the gradient, yeah? We started looking at those gradients. So then when we get down here, we get into the derivative. What does it represent? Well, since we started with the gradient, that's what it represents. It represents the gradient of the function. All right, and that's a key thing. Newton, when he did it, he talked about it as rates of change. In terms of us, if we talk about rate of change, it's the gradient. How much does the y change when the x changes? Something that's got a steep gradient, change the x and the y changes a lot. Something that's got a small gradient, change the x, the y changes a little bit. All right. We're all good so far. Yes? All right, so that's the theory behind this derivative. So if we want to find the derivative of something, we need to use this here. And let me just rewrite it. Up here. So for the derivative, for the function f of x, oops, not u, not I, function f of x, the derivative is written f dashed x, so this little dash up here means derivative. Alright, so f dashed x equals the limit, h tends to 0, f of x plus h minus f of x over h. How are we going so far? Alright. Alright, now this next bit that I'm going to do, normally, if we have lots of time, in non-COVID years, we spend a bit of time getting you guys to do this, but I'm going to do it as an example today. All right. So, if we want to find out, for example, find the gradient of gradient/derivative of f of x equals x cubed by first principles. I've used the right principle, let me check all these words. No. There's the wrong one, LES. So this process that I'm going to do is what's called finding it from first principles. And normally, as I said, in non-COVID years, we'll get you guys to do this. But I'm going to do it. All right, so it says find the gradient/derivative of fx equals x cubed by first principles. All right, so first principle says f dash x, which is the gradient or the derivatives, is the limit, as h tends to 0, of f of x plus h minus f of x all over h. So our function is x cubed. So the limit as h tends to 0 of f of x plus h, so I've got to replace x by x plus h and cube it, because that's our function is cubing. We've then got to take away the function with just x, which is x cubed, and that's all over h. All right, so the next bit we've got to do is we've got to expand that. I'm going to do that over the side here. So x plus h cubed would be x plus h times x plus h times x plus h. I'm going to leave this first x plus h where it is and expand these two. So x times x is x squared. X times h is xh. H times x is xh as well. And then we've got h squared on the end. So I've got two lots of xh. So I now end up with that. I'm now going to multiply this second bracket by this first one. So multiply the x in and you get x cubed plus 2x squared h plus xh squared. Then multiply everything by h, and so I get x squared h, 2xh squared, and h cubed. And then, when I collect my like terms together, I get x cubed plus 3x squared h plus 3x h squared plus h cubed. All right. give you a second there to get that down. All right, anything that we need clarifying there at the moment? No? All right, so this stuff, all of this stuff here is this. All right, so now I'll put that in there. So this is our first principles process. All right, so I've got x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed. All right, anyone notice anything there? Oh, I forgot my h on the bottom, other than that. The x cubed, you got a plus x cubed there and a minus x cubed. So, all right, what else do you notice? Anything else about these three things? They will have h's, exactly. So I can take it out as a common factor, so I'll take that out, h goes out, and I've got 3x squared plus 3xh plus h squared over h. All right, good. What else? What do we notice now? The h's can cancel, yep. All right, so now we've got the limit as h tends to 0 of 3x squared plus 3xh plus h squared. All right, one last step. Now we need to say, all right, we've got these three terms. When h goes to 0, so changing the h, making it go to 0, what effect is that going to have on each of those terms? So if I change h and make it smaller, is that going to affect this term at all?
No.
No, because it hasn't got an h in it, has it? What about this one, 3xh? What's going to happen to that when h gets smaller and smaller? It's going to go towards 0, yeah, because h is going towards 0, and 0 times anything is 0. And this one, of course. So the limit, as h tends towards 0 of all of that, is simply 3x squared. And so 3x squared then is the derivative of x cubed, and this process here is called first principles. Called first principles because that's where it comes from. Now, there is some good news. The good news is maths about patterns, and there is patterns involved. So, and there's patterns for all sorts of functions. The ones we're going to look at is just polynomial functions this year, but there's all sorts of functions. And we get those patterns not from just chance, but by doing this. And as you can see, it's quite time consuming, isn't it? A lot of stuff to do the first principles. But there is a pattern. So for polynomials, let's have a look. Look at what we started with. We started with x cubed. Look at what we finished with. Finished with 3x squared. What things do those two have in common?
X.
They have x in it, yep. What else have they got in common?
They've got a power.
They both got a power. What do you notice about that power?
It's one.
This one's one less, yep. What else do you notice?
Three
The 3.
is in front.
What was the power? Where is it now? In front. All right, and so that is the pattern. When we go from here to here, this power goes out front and we reduce by 1. Much easier than doing that first principles, yeah? But we need to do the first principles first, then we notice that there's a pattern. And now we use the pattern. So, let me write that down. So, for polynomials. Derivative pattern is so if fx equals x to the n, then our derivative f dash to x is x to the something. So what did we say happened to the power? It went in front, and this one here, this power of our derivative is 1 less. All right, so let's have a look at an example. X to the 10.
10x to the power of 9.
10x to the power of 9, yep. So that 10 comes down the front, and we reduce our power by 1. It's 10x to the power of 9. Now, can you imagine how much work that would be
Yeah, because it's 10.
to have 10 brackets to expand and collect your... it'd be a huge amount of work. So, because maths is about patterns, and plenty of people in the past have done that first principle and discovered that's the pattern. Yes, Emily?
Does it work for all of them?
Every polynomial.
Okay.
Other functions would have their own patterns, but polynomials, this is the pattern. Yep. All right, so if we've got something with a number of terms, what we do is we look at each term individually. So the x to the 5 part, what would that become?
5x 4.
5x to the 4. Whoops, not equals, minus. Minus. We've already got this 2 there, so that's 2 times that. So let's leave that there. And the x squared becomes 2x, yep, 2x. 2x to the 1, of course, but normally if it's x to the 1, we don't worry about writing that. This next one here, remembering that's x to the 1.
There's no x.
There's no x, so do you reckon just plus 3?
Yep.
Great idea. So what we've got is just a full explanation. We've got x to the 1, so we bring that 1 down. Reduce it, x to the 0. X to the 0 is? Anything to the 0 is?
Nothing.
No, not nothing. 1. So you got 1 times 1. And then of course we've got this 3 here already, so there we go. And what about a number? What do you think is going to happen with a number?
Nothing.
Nothing?
Same.
Gone.
No, just plus 2.
Plus 2? Plus 2, that's one suggestion. Any other suggestions? Minus 2? Alright.
Okay, is it, did you say plus 3?
Plus 3.
Plus C.
No, not plus C, that's integrating. You're going the wrong way. Head of yourself. Alright, let's think about it this way. I could multiply that by 1. And instead of writing 1, I'm going to write x to the 0, because x to the 0 is 1. I bring my power down, 0, x to the minus 1. We're multiplying by 0, so it's just 0. So any numbers would be plus 0 on the end. Alright, minus 4 there, plus, whoops, minus 4x, plus 3. Alright, anything I need clarifying there for anyone? No? Alright, that's a fair bit to get our heads around today. Yep, so I hadn't planned on doing any examples and starting on any work. I plan to do that tomorrow, so I think we will stop that there, and then tomorrow I'll do some examples. I'll record again some examples, and then we'll spend the time working on it. Right. Yeah, I know there's not any here tomorrow, so.
Oh, true.
All right, so I will stick that video up on YouTube, and I'll do the same tomorrow.